Section 5.4 is on working with integrals, and it has a few tricks, especially dealing with integrals of even and odd functions to begin with. So if we have an even function, remember that even functions are those that are symmetric across the y-axis. If I want to integrate on a symmetric region, so I am going from negative a to a, so I'm looking at the same distance on both sides of the x-axis right here, then since I have the same amount of function area on both sides, instead of doing the full integral from negative a to a, I could do twice the integral from 0 to a. So I could just double the positive half, and then I'll have the full integral. Okay, now if it's not an even function, if it's an odd function, then you normally have the positive and a negative section to reflect across the origin. Whether you're in quadrants 1 and 3 or if you're in quadrants 2 or 4, they're going to be opposites. So if you're going to integrate between symmetric bounds, negative a and a, your integral will be 0. So odd functions, this is even better. I don't need to worry about doing just the positive half, although that can be convenient. Plugging in negatives can cause error. But if I have an odd function, the integral is just going to be 0, and that's really much simpler than having to do all the work of integrating if I notice that my function is odd. Now it only works, of course, on symmetric bounds, but that can still be useful for simplifying some integrals. All right, so in the example at the bottom, we want to use symmetry to evaluate. So in the first one, this function is even, and so since it's going between symmetric bounds, negative pi fourths and pi fourths, I can illustrate this. So on the cosine graph, pi halves would be there, so pi fourths is here-ish. And so instead of integrating the full region from negative pi fourths to pi fourths, we're going to integrate twice in the positive region, and so that's going to give us the same thing. So if I do the positive region twice, I should get the total area. Okay, so we'll do that. We're going to integrate from 0 to positive pi fourths, and we're going to multiply it by 2 of the cosine x dx function. Now, advantage of this is that it's usually easier to plug 0 into a function than it is to plug in other numbers, so that helps us on that. So we've got 2 times the integral of cosine is sine of x, and now we're bounding it between 0 and pi fourths. So that's 2 times the sine of pi fourths minus 2 times the sine of 0. So 2 times the sine of pi fourths is root 2 over 2, so 2 square root of 2 over 2, minus 2 times sine of 0, and sine of 0 is 0. So I end up with the square root of 2 for our area. I could have done it with those original bounds. It just wouldn't have had something come out as 0, making one part of it easier to calculate it. Not a big deal. So it's not as helpful for an even function, but it is still helpful because it's easier to plug 0 into most functions. If I look at the next one, because this one is odd, if I want to integrate from negative 200 to 200, now I'm not exactly sure what negative 200 is on the scale. Let's say these are going by hundreds, for example. Then this would be negative 200, and this would be 200. It sounds reasonable. And so the two areas are going to be crossing each other out because they're the same, but one's positive and one's negative. And so because it's an odd function, this is going to integrate to 0. And I'm done. I don't have to do any integration work there. If it's an odd function, it's going to integrate to 0 over symmetric bounds. They have to be negative 200 to 200. I couldn't have done negative 100 to 200, although there are some ways you could split that up and use some properties. But right now, I want them to be exactly the same to be able to eliminate to 0. Okay, so that was our first topic. The next piece is going to have us look at the average value of a function. Okay, so the average value of a function. Now, usually when we compute an average, we find a total and then we divide it by the number of items. That's how we would do an average. If I want to do an average of a grade, we're going to take a total and we're going to divide it by a number of items. So we need to expand this just a little bit. When I find an average, I'm finding one value that sort of represents all of the however many values there were. So I can do that for grades, I can do that for heights of a function as well. So if I found the total area of a rectangle, and just in general first, if I took the area, which was, instead of calling it length and width, let's call it height, since this is called height right here. Let's call it height times width. If I took area and then divided it by width, that would give me an expression for height, right? And so what I want to do then is talk about the net area of a rectangle. And so if I divide off the width, we can calculate the width of this rectangle as b minus a. That's the width, right? And I know the area is the integral. So the net area is going to be, instead of writing it as a divided by w, I could write it as 1 over w times a. So 1 over w, b minus a. And then area is the integral from a to b of f of x dx. Okay, so this is how I would represent height, the average height of this. Actually, this box was for net area. That's okay. I went and did height. So net area is the integral from a to b of f of x dx. And so if I divide that by width, this is going to give us height. And so we went ahead and built the whole formula right there. Again, looking at the two pieces, the average height, we use that bar on top of f to mean f average. The average height of a function, we divide by the width, and we have the area divided by the width. So that would again be area divided by width equals average height. Okay, so area is the integral, 1 over b minus a, that's just dividing it by the width to get the height. Now, the average value formula can be useful in any kind of situation where we're not just looking at height, but if I know what the function means, it can be finding average velocity or finding average cost if it's a cost function. So let's take a look at an example of finding an average value. Find the average value of this function on the interval 1 to 2, draw a graph and indicate the average value. Okay, so first of all, I'm looking at from -1 to 2. And so the average value won't just be the average of these two heights, which look like, I don't know what the scale on this is, maybe by 2, so -16 and 5, -11 would be the average value of just those, but it's going to be pulled up a little higher than that for sure, because there are more values in the low space up here than there are down here in this tall negative. So it's definitely not the average of those two. I might not have gotten right there, but not the average of just the two y values. Okay, so let's try to find it. So the first thing I need for f bar, it's 1 over b minus a times the integral from a to b of f of x dx. So I'm going to actually write it down here so I have more space. So 1 over b minus a, so that's 2 minus -1, times the integral from a to b, so from -1 to 2, of x to the 4th minus 4x to the 3rd dx. So I have 1/3. Now I can do the integral. So I'm going to have a antiderivative here of x to the 5th over 5 minus 4x to the 4th over 4. We're adding 1 to the power and dividing by the new power. And then bounded between -1 and 2. It's not necessary to write the extra bar if I already have a bracket, so I used brackets instead of parentheses. So I can just assume that that is going to have the bar built into it. Now we're going to plug in top bound minus bottom bound and get that average value. So 1/3 of, and we have our 2 to the 5th over 5. The 4's cancel right here, so I'm not going to bother writing them down again. This is just going to be minus 2 to the 4th. Then minus 1/3 of 1 to the 5th over 5 minus 1 to the 4th. Okay, so we have, again, we just need to compute this as a fractional value. So a calculator is fine to use. If I can find mine. There it is. So I'm doing 1/3 of 2 to the 5th divided by 5 minus 2 to the 4th minus 1/3 of 1/5 minus 1 to the 4th. So I just wanted to get that as a fraction, so that's negative 44/15, or if I round that off, it's negative 2.933. Okay, so back up to our graph. The average value is, these are by twos, I think. So 2, 4, 6, 8, 10, yes, 2. So right about there. So the average value is realized right here, which is definitely not the average of just these two y values. The average between these two y values, again, if I calculate this one is negative 16, and that one's about 5. So they're 21 apart, so negative 11. So my scale is a little off because I forgot that was by 2. That was close, though. So that would have been if I just averaged the two of those. And we're definitely skewed upwards on this because we have so many values that are small compared to the ones that are large negative. So the average value happens up here. Okay. So it takes into account all the y values of the function and how many of them there are at a certain height versus just the individual y values themselves.